Could you unpack a little bit more for the audience, just because some people are coming in without a lot of experience in calcium imaging, and
Sure.
and what would be the ramifications of having this sort of worse than expected coupling between spikes and calcium signal in terms of understanding the brain or in terms of building decoders for BCI?
Sure. So I think one thing we'd like to do in neuroscience is have a record of the electrical activity in populations of neurons. So we'd like to know for tens, hundreds, maybe even thousands of neurons, how many spikes were in each one of those neurons. And there's a lot of different ways to get that sort of information. The gold standard for a long time was electrophysiology. So you could either, basically stick a wire near a cell and record those spikes. And in electrophysiology, you have one major advantage, which is you have really good timing. So you know exactly when those spikes occurred. There is a disadvantage. You don't know exactly where the neurons are that those spikes came from. So with electrophysiology, you have a spike sorting problem in terms of figuring out which spikes came from which neurons, because you're literally blind to it. You have a wire in the brain and you're recording a signal. Now, of course, you can stick lots and lots of wires in the brain. We can get arrays. You can get, neuropixels, shafts with arrays of recording sites, but you still fundamentally have this problem. So there's obviously been an optical revolution in the last 10 or 20 years where we can use calcium imaging as a basically indirect readout of the electrical activity. So when a spike happens in a neuron, a lot of calcium ions rush into the cell. And because it's floating around the cytoplasm, it's a big signal. It's a big change in concentration. We have now very good indicators of that calcium. And therefore, we can record with imaging methods the calcium in a neuron as an indirect readout of that electrical activity. So now you can imagine you've got a whole you're literally making a movie of a field of view of many, many neurons, tens, hundreds of neurons, in order to get a record of that spiking activity in that population of neurons. And now you have a different problem. We actually have two problems. One, you don't really have good timing precision because calcium is a bit slow and the indicators are a bit slow. And the second problem is there's not a direct relationship. Well, there is a direct relationship between the calcium and the spikes, but it depends on the amount of indicator in the cell, depends on the biophysics of the cell, and it depends on how well you're sampling that cell. So if you want to image more and more neurons, you've got to go over a larger and larger field of view, and you get less good information about each cell. And that's what they quantified pretty well in this Allen Institute paper. They quantified sort of as you zoom out and you get more neurons, what effect does that have on how well you can read out the spikes? And to sort of try to wrap up here, because I know it was a bit of an extended answer, but in sort of trying to get at, we want to decode the activity of neural circuits. It doesn't matter if you're doing electrophysiology or calcium imaging, you want to know precisely how many spikes occurred in all those neurons. And so you can imagine as you want to get more and more of the population, you want to understand more and more of the neural circuit, you might have to pay a cost of not understanding each neuron as well. And that's what they quantified well, is that trade-off between more information, but maybe at a bit less quality.